Hello, mentors. Welcome to meeting 8, August, March 2nd. And so we have two activities in this meeting. So the first one is called alga patterns, which goes from 220 to 310 or so. And then at 310, you can start a coloring puzzles, which is a very short activity in the sense that it's very modular. You can just do it for fun and just take your time and really have fun at the end. So at the end we'll may also have just a closure depending on your room, so it may be a little longer. It will depend on your leaders. So that's another reason why these coloring puzzles, we made it so that it's very modular and it can take from maybe even 10 minutes to the whole maybe 30 minutes that we anticipate. So as usual, some tips for time management. So the first alga patterns, you expect 50 minutes, but you can easily go to 60 minutes, just 1 hour, maybe have a little break in between or so. And then the second one, as we said, expect 30 minutes like at most, but you can really reduce it if you want. The principle is asking thinking questions. And again, do not show teaching manual to students. Part one may have some time-consuming computations because we're doing fractals and it's a lot of generating new cases. So that's totally fine. Be ready just to assist students in giving them tips to be more efficient. So don't spend much time just in the computations, but give tips on how to compute, say, 11 times 11 in a fast way, or mental math, etc. Still doing the computations, you cannot avoid it. It's part of the problem. That's part of the math. Part two, as we said, it's a series of puzzles, and there's no need to do them all. You can just ask students even to complete them at home and to return in spring with some of them even. So let's dig into the activities. So alga patterns, let's look at the thing. We start with a notice and wonder. What do you notice and what do you wonder about these patterns? And students may say, okay, I noticed some red and yellow things, which will be nodes or cells. I also notice some connections. Kids may notice from here that every red gives rise to a red in the next level. So upside, growing upwards. And then each yellow gives rise to 3 cells, 1 yellow and 2 reds. So they could also notice that, as you grow, this never ends. You will get much more red cells than yellow cells. And they could wonder if they can change the rules, or they could wonder, what does this even mean? So many, even non-mathematical questions that just can increase motivation. So instead of just explaining all the rules from the beginning, make sure you spend at least 5 to 10 minutes in this notice and wonder. It's really powerful, really effective, but you have to give time to students and guide them, with follow-up questions or with, clarifying things. You meant this or that. Then you go to really more technical exploration. So you actually do tables now and keep track of the numbers. So you give this pattern one, which start with a yellow, and then each yellow gets 1 yellow and 2 reds, and each red gets 1 red. So the levels grow, we go upwards. So it's like an upside down tree somehow, or alga, I guess. And there's branches, there's nodes. So it's really a graph. This is what we call a tree in mathematics. So it's a graph that has no cycles and it's connected. Everything is connected. And you start counting the patterns. So at level 0, there's just 1 cell. At level 4, how many cells are of each color? So you notice that the red cells grow by 2, so 0, 2, 4, etc. Yellow never grows, it's always 1, and you can reason out why. And there's a lot of induction in these type of activities, because if something happens at some level and you can prove or you can convince the student or the mentor that it keeps going on, it keeps being valid to one level, from one level to the next level, then no problem, it will always be true. And this level of reasoning, it's fine for this, middle school. You don't have to do formal induction or anything, but you really want to reason why you keep, preserving some of the properties, why it's still valid. So show me why, if it happens at level 4, it's still valid at level 5, what happens at level 6. So I think really the key is to connect the levels. So always when you analyze a level, analyze the next level, or maybe the previous level, or maybe even go 3 levels, because that's really the seeds for induction. You're really investing in inductive thinking without even doing formal induction proofs. Then you ask that the alga needs, and second question, 1,000 red cells or more to survive in level 100. Are they going to be able to do that? Why or why not? So this question just, is just to prove or to transfer the knowledge from part one, and just to see that it grows by 2. It's a linear pattern, but it will really not be able to do it, at level 100. You always have 200, but no more. So the third question is very interesting. It's about accumulating cells. So the pattern is linear, and it's very easy for the total cells on each level, but it's not as easy if you talk about accumulating cells. And then we get into a very interesting, and let me show you quickly the solutions, into a very interesting pattern, or accumulating cells, in which you get the perfect numbers, the perfect squares. So you get at level 0 just 1 cell. At level 1 you have 4 cells accumulated, right? So looking at all levels below plus the level that it's current. Level 2 you get 9 cells. And then it's a reason on why this happens. Why do we get these, perfect squares, 1, 4, 9, 16, 25, 36, and so on? And the reason, again, it's inductive. So, here the way to show this is doing these grids or these squares that are growing in a very nice way, adding odd numbers each time, so that if you already had a square number like 16, say, or that like 9, and you add the next odd somehow, then you're still getting a square number. So this is really nice. It's very, very nice. And this will be the pattern. Then you get into other more interesting even activities, which is mutations. So you want to create a mutation in the rules to get more red cells. So this alga as a biological species was not so efficient because they didn't really get all the cells that these alga needed. So you change the rules, keeping in mind that you still start with 1 cell. Each yellow still generates 3 cells, and each red still generates 1 cell. So it's very interesting things, because you really want red cells, but red cells don't really have too many babies. It's only 1. And yellow cells, you don't really need them as your final goal, because you need red cells. But the yellow cells generate a lot of babies. 3 babies per level, right? Per new level. So you want to change the rules in any way you like and compare with the previous alga. So this alga, it's called now pattern XX, which will have another base, maybe yellow or red, and it will have some fixed generating rules. So the question here is really important to explore. This is really an exploratory activity. Did you get more red cells than your previous alga? Which patterns can you see? Maybe they can even change the alga again. So that's the mutations for question 4. And then the last part of this activity, alga activity, is called pattern ultra. So we still want more red cells in level 100, but now we'll have more power. And so we have this concept now of DNA tokens, which we have 6, which are really, how many tokens you have to build your generating alga. So you start with as many cells as you want, and kids may want to start with even 3 or 4, but each one that you put costs 1 of these 6 tokens. Okay, so you have a fixed amount of resources, just 6, and you see what happens. Each yellow cells can have as many babies as you want now, so now it's more free, but each will cost 1 token. And now for the red cells, we just put this restriction to make it more interesting, that you can have at most 2 cell babies for the next level, at most 2. Remember that in the previous part, it only had 1, but each will cost 1 token again. Here's one example. I could start with a base with yellow, red, red, and then generate a yellow, generate red, green, red, yellow, sorry, and a red generate another red. And I count 1, 2, 3, 4, 5, 6. So that's totally valid. I could even change this base, like only having 2, and maybe having the red generate more red here. So I can do whatever I want when generating these patterns. And then the question is about comparing your alga with the ones from your partners, which seems to be the best in terms of number of red cells. So this is an optimization problem in which you have an initial condition and some generating rules. Of course, you cannot just say red, red, red forever. You have some limiting condition, which is here the tokens, only 6 DNA tokens. And then it's about exploring and maybe changing the rules and seeing what happens. Then analyzing some general conditions of what is best. So here I think we learned that you really don't care much about the initial conditions, but more about how fast you wanna grow. And you wanna grow also yellow cells, because yellow cells can have many babies. So many babies will be red. So lots of interesting stuff going on here. Let's go to the second activity and very quickly, say what it is about. So it's coloring puzzles. So we have fractions, fractals, coloring. We have a lot of patterns, beauty, creativity, and also patience, because, well, we have to count many things. So as we said, these are very modular and can be done very quick and very relaxed. So you start with this picture, which is frame, which is a 1x1 big square, say, which has a lot of partitions, right? So it half here, and then a fourth here, and then 1/8, 1/16, and so on. It keeps breaking. And then you color as you want, and then you just say what fraction of the total is colored. So this is very nice activity, because even if kids are not really getting the concept yet, they can just color, say, the left and just say 1/2, and then go from there. Some other kids that may be more adventurous may just do some other crazy coloring. You can only use one color, that's the rule, so that we don't get into counting which color or which other color. So it's like a binary problem in that sense. And then you get into other type of activities. So now you color these 3 frames, A, B, C, and then you secretly write the fraction that you colored. Then you exchange this page or this manual with another student to see if they can guess the fractions that you color. So you get into nice interaction, like a nice detective game, in which you will validate the fraction, the secret fraction. Then you get into thirds, and it's the same idea. You color 1/3 in several ways, and how else could you do it? So, of course, trivially, you could just color, of course, all these squares here that constitute 1/3 of the whole picture, and that's one valid way. That's no problem with that. But the question is, how else could you do it? So maybe you could color here, and you say I have 1/3 out of the diagonal, and then of whatever's left, I should maybe cover 1/3. So lots of interesting discussions here to be done. So that's the meeting, and it's important to remember it's the last meeting, so you want a more special closure. You can tell the students that we'll meet you again April, and we really hope you to, that you guys, you mentors are back with us for spring, which we'll do the same kind of explorations with more magic and more creativity, and of course welcoming the kids to UCI, hopefully. So have a lot of fun.